Hello, students. Hello, students. Now, originally, I planned to talk about exam focus exercise tonight, but I realized some of you didn't have the opportunity to finish. So my suggestion is first you finish the exercise, you hand it to me, I will mark it, and then you can watch the explanation on every question. I will talk about every single detail in that video. The video has already been uploaded in the Google Classroom. Okay, today we have a huge task. I plan to finish 6.3 tonight. So are you ready? You should be prepared with the notes, and also just always write very fast for tonight. Let's have a recap. On Wednesday's lesson and Thursday's lesson, perhaps even Tuesday's lesson, I don't remember because this week everyone is very busy. On 2 days of this week during the lesson, we only finished half of this lesson, half of this part. The second derivative and point of inflection. Now, like I said, I will have a recap. I will do a recap because I didn't record the lesson on one of those days, and I don't remember which day. And some students may need to study from the beginning. The concave and convex, this concept, if we're talking about in an actual object of substance like the lenses, it's obvious which one is convex and which one is concave. Even with the polygons, I think it's very clear, and it's easy to understand that some having an indent is called the concave, and the ones that don't have indents are convex. But with the, if we're talking about a curve, it makes no sense to say concave or convex. It makes no sense because from where you're standing, it could be concave or convex. So how do we define the concavity of a curve? You have to jump out of the concept of convex and concave and try to understand a whole new thing. In the textbook, it's shown the two examples. And the one is concave and one is concave up and one is concave down. We actually don't use convex anymore. Both of them are concave. One is concave up and one is concave down. And there's no explanation to it. It's just like, oh, one is bending towards upward, one is bending downward. But what is bending upward and bending downward? Like this is bending upward. This is also bending upward. But this one is not straight up. It's still up, but not straight up. This one is bending down. This one is also bending down. Right? So how do we define it? And during the lesson, I wasn't very clear, but this time I'll try to be very clear about it. To determine which one is concave up, we mustn't look at just the curvature of this curve. It's not a geometry thing. It's not. It's a value thing. What do I mean by value? I will calculate the value if this is the curve f against x, and then I can draw, perhaps I can draw it here. This is 0. This is negative. This is negative. At A is negative. At B is positive. I'm talking about the f prime. This is f prime. I mean, the value of the derivative, the value is from negative to 0 to positive. Now, which is very different if you look at this concave down curve, because this one, it's from A positive to here negative and to B negative. You see, it's a very different curve if you think about the value of the derivative. But this one, both of them are concave up. You will see, oh, this is a negative, and here it's 0, and then here it's positive, and here is more positive. You see, it's still, I mean, it's not exactly the same as the other concave up one, but it's still, the first derivative are very similar with these two concave up curves. Now you can see the first derivative is increasing on the concave up curve throughout, whereas the concave down curve have a decreasing slope. So you see the concept of concavity is from the value of the derivative, whether or not it's increasing. So I repeat myself again when I say, oh, if you have a circle and we agree on the circle, every place has the same geometry, doesn't it? It doesn't. It's not a different curve at every single part. It's not a different curve. So if you're looking at from a geometrical perspective, it's the same. It shouldn't have different concavity if concavity is a geometrical concept. But concavity is not a geometrical concept, because the upper half of the curve is concave down, and the lower half of the curve is concave up. You see, because the value for the upper half, the derivative is decreasing. For the lower half, the derivative is increasing. Here, I'm talking about from the left to the right. I always talk from the left to the right when I say decreasing, increasing. I mean, oh, when you look from the left to the right, you know what I mean? So that if you understand this, and then you truly understand the concept of concavity on curves, and then compare. Now, do a final compare. Now, what is concave lens and concave polygon? They are not, this concept, when I say concave, I'm not talking about the value of the lens, the value of the polygon. It's not, there's no value. But the concave up curve and concave down curve is because of their value. Look at theorem 6.3. If the second derivative is positive, meaning the first derivative is increasing, it's a concave upward curve. If it's negative, then it's concave down. There is a note. It says that this theorem cannot be said backwards. I will talk about this note later on in today's lesson. Example 7, how to find out which range the curve is concave up, which range is concave down. In your exercise, you won't be given a curve, so you can observe easily. So you will derive, derivative, second derivative, and then you will list out the positive or negative the signs as follows, and then you will answer, oh, for this part, for x is greater than 0, it's concave up, and the other part is concave down. As shown in the graph, this part is concave up, this part is concave down. The second derivative test is based on concavity. Because we know the minimum, this point must be lying on a concave arc curve. And this one must be lying on a concave down or concave down curve. Example. Example 8. How do I find out the stationary points? I will solve first derivative equals 0. And the answer is the stationary point. Now, how do I decide whether the stationary point is a maximum or minimum? I can have a test called the second derivative test. If the value at the stationary point is positive, like in this case, it means the curve is concave up at that point. It means that stationary point is a minimum point. Example 9. Maybe I'll show the classwork here. Example 9. It's given that the curve is this. Find the stationary points. A, y prime equal cosine 4x times 4 divided by 2 minus 1. Okay, so solving y prime equals 0, I have cosine. Maybe I simplify a little bit. It's 2 cosine 4x minus 1. So 2 cosine 4x minus 1 equals 0. Cosine 4x equal 1 over 2. I need to solve this equation. Anyway, remember this. If you don't remember, it's okay. I will help you remember. First, you will find a reference angle alpha. A reference angle alpha. From the calculator, you will get 60 degrees. But you don't use 60 degrees. You don't say it's 60 degrees. You will talk about the range. Because 0 is smaller than equal to x, smaller than equal to pi over 2. Therefore, 0 smaller than equal to 4x, smaller than equal to 2 pi. You will find the range first. And inside this range, you will find a few angles satisfy this equation. In this case, you will get 4x equal the first angle, pi over 3. That is equal to 60 degrees. Always use radian. Always. You see, there is no degree here. No degree. That's the first angle. The second angle is the angle in quadrant 4, which is 5 pi over 3. If you don't remember, one angle is here, 60. The other angle is here, 300. Both of them have the same cosine value. X equal pi over 12, or x equal 5 pi over 12. Now, the stationary points are at these 2 points. I don't know maximum, minimum, or saddle point. I don't know, but they are all stationary. So, when x equal pi over 12, find the value of y. y equal sine pi over 3 divided by 2 minus, this is root 3 over 4 minus pi over 12. The second, when x equal 5 pi over 12, y equal sine 5 pi over 3 divided by 2 minus 5 pi over 12. It's negative 3 over 4 minus 5 pi over 12. Okay, so the stationary points are first one, pi over 12, comma, root 3 over 4 minus pi over 12. Second one, 5 pi over 12, comma, negative root 3 over 4 minus 5 pi over 12. Now, you are not given the graph, but on this graph, if you have one, you will see one here and one here. Now, because this curve is bounded, is defined from 0 to pi over 2. So I only show you from 0 to pi over 2. The other parts are not included, although they exist, but they're not included. So I don't need to think about, oh, there are others outside. There are, but not our answer, okay? Second, can we test whether or not it's a maximum or minimum or saddle point? We don't know. We don't know. So how do I test? Part B. The second derivative test is the quickest way I know. So second derivative first, it's 2 negative sine 4x times 4 minus 0 equal negative 8 sine 4x. Because y prime prime at x equal pi over 12 equal negative 8 times sine pi over 3, it's negative. And this one, x equal 5 pi over 12 is equal to negative sine 5 pi over 3 is positive. Now you use the calculator to find out. I just know. You should know as well because this is quadrant 1 and quadrant 4. Anyway, one is negative, the other one is positive. A negative one means it's a concave down curve. A positive one means it's concave up curve. So the first point is a maximum point. While the second point is a minimum point. And it's there on the curve. You see this is a maximum and this is a minimum. Okay. Hey, sorry, my face is in the way. Now you can do the exercise. You can do the exercise. And when you're done, please let me know so I don't wait. Sophia, Cassandra, Mavis, Gladys, Melissa, you need to be quicker. Okay, look at the answer. Now, I know some of you are starting to worry about the exams now, and then you don't want to exam on chapter 3. But it's okay, girls. Last year, you've done so much exercise on chapter 3. So a little bit exercise will remind you what it is, like this one. You do the derivative, and then you solve this equation, and then the reference angle, and these are the two answers. There are two stationary points, as you can see on the curve. Part B, do the second derivative, and then do the second derivative test. If it's negative, it's concave down. The point is a maximum. The other one is a minimum. That's it. Let's have a recap. I don't know. Now, there is one example talking about how to determine concavity. Now, how to determine concavity, there is no maximum minimum. It doesn't have to be a maximum minimum. You see, the whole way this is concave down, but it doesn't have a maximum. This is concave up. It doesn't have a minimum. First example, how to determine concavity. Second example, this example, how to use concavity to determine maximum or minimum point. Example 8, find the stationary point, determine. Example 9, find the stationary points, because there may be multiple, and then determine. The same, basically, the same as example 8. But the function is not a polynomial, so it's harder. Now, what are we going to talk about next? The next part is very hard because I'm going to address the notes. The notes here in this one sentence saying that this one, not the notes, this one. It says that the second derivative test can fail if you find the second derivative equals 0. Now, because if you think about it, if it's negative, it's a maximum. If it is positive, then it's a minimum. But how about it's not positive or negative? What about the second derivative is 0? Is that possible? I say that the second derivative, sometimes it's 0. Okay. What does that mean? Can I say, oh, is it maximum, minimum? Obviously, it's not so easy anymore. Well, it means that the second derivative is a failure, and then you need to use some other methods to solve the maximum or minimum problem. Now, why is it a failure? I need to explain. Why is equal to 0 why equal to 0 means it's a failure? Look at this part. Inconclusive second derivative test. Inconclusive means the test is not useful. The result is not applicable. I will show you one example. This example is a polynomial. I think it's three polynomials. 3 polynomials. The first one is x to the power 4 plus 1. Okay? And then you can see the second derivative is 12x squared. And the second derivative at 0 is 0. At that point, this one point, the second derivative is 0. And from the graph, we know it's a minimum. Second example, y equal negative x squared x to the power 4 plus 1. In this function, the second derivative is negative 12x squared. The derivative, the second derivative at 0, 0. But you can see this point is a maximum. Last example. F of x equal x cubed plus 1. The second derivative is 6x. Second derivative at 0 is equal to 0. All of them, 3 of them. All of them. The second derivative at 0 are all 0 in value. Well, all equal 0. 0, 0, 0. But in the first function, it's a minimum. The second function is a maximum. The last function, it's a saddle point. I think that is enough to say if you find second derivative, if you find the second derivative at a stationary point is equal to 0, it means nothing. It means you need to redo. And does that happen very often? Not very often. Not very often. So you still should try to use second derivative test, but only redo if it fails. I'll show you an example. Example 10. Find the local extrema. Extrema means maximum minimum. Yeah, maximum minimum. Find local extrema. I'll do the first derivative. First derivative. I'll do the second derivative. Okay, I will solve f prime equals 0. 3x squared plus 4x cubed equals 0. X squared plus 3 plus 4x equals 0. X equals 0 or negative 3 over 4. That means here there's a stationary point. Here there's a stationary point. Stationary. Okay, now how about, is it maximum, is it minimum? How do I know? Test. For this one, equal 6 negative 3 over 4 plus 12 negative 3 over 4 squared. This is equal (2.25) is positive. The first one. Okay, and then you can find f of negative 3 over 4 equal negative 3 over 4 cubed plus negative 3 over 4 to the power 4. Negative 27 divided by 256. Therefore, negative 3 over 4. Should I answer the point or the value? I should answer the value. The value. So, the local minimum, because this means minimum. So, the local minimum at negative 3 over 4 is equal negative 27 over 256. Now here I realize I need to answer a value, the local minimum value. That's this one, minimum. The other one, f prime prime at 0 is equal to 0. What does that mean? Is it maximum? Is it minimum? Is it saddle point? We don't know. Some students think, oh, if it's 0, then it's saddle point. Like I said just now, could be anything. Could be anything. So you have to do the first derivative test. X first derivative. X smaller than 0. X equal to 0. X bigger than 0. Okay. And then you just put in a value that is slightly bigger than 0 and then test. Test. I think it's factorized. It's easy to factorize. Oh, not this one. The other one. This one. Not the second derivative. The first one. Take out x squared and then 3 plus 4x. It's easy to see whether or not it's positive or negative from the factorized because I can look into each individual factor. So if the middle is 0, smaller than 0, this is still positive and this is still positive because x is very small, small. Smaller than 0 doesn't mean -1. Gross. Smaller than 0 means a little bit smaller than 0. From the graph, you should test here a little bit smaller than 0, not -1, because -1, if you test -1, the -1 will be here. The -1 is not in the range between 0 and the other stationary point. You should choose a value that is very close as long as it doesn't pass to another range. So it's still positive. And then this side is positive. Remember? It's not just, oh, it's smaller than 0, then it's -1. It's not. That's not. Here you should use maybe -0.1 to test. The key is do not go far past another stationary point because you're testing the other side. I'm testing here. I'm testing the derivative here. I do not want to test the derivative here. Okay? So it's positive 0 positive. And last time we talked about it, it's positive 0 positive. That means this point is a saddle point. So that means F0 is not a local extreme. It's not maximum or minimum. It's neither. Or you can say, oh, it's a saddle. But now I don't think you say it's a saddle because a saddle point is a point. This is a value. So you say it's not a local extreme. Or you say it's not a maximum or a minimum. Then you do the classwork and then you let me know. Let me know. Millie Chan, Wendy, Mavis, Gladys, Sophia, May. Okay. Now this is the answer. Y prime. Now some students like to write equal to 0 directly after the differentiation. I do not. And when I solve the equation, sometimes like this, I don't know if you write it out. You can if you know. The first factor can never be 0. We had this in the exercise in the exam focus earlier. And then here looking like I did nothing, but I'm doing the second derivative. And then the second derivative test failed. It's fine to leave it there, even if you find, oh, it's not inclusive. Oh, sorry, it's not conclusive. Not conclusive. And then you go back to the first derivative test. And it's very easy to test. And it's a minimum. So you say the minimum is 1. The minimum value is 1. Now, girls, it's very easy if you have the curve to help you, because you can check, oh, this is the minimum. Of course it is. But if you don't have the curve, believe me, because it's not so easy. Next. Almost there. We're almost there. In this lesson, we will talk about the points called point of inflection. What do you call it? A point of inflection. Meaning there is a curve, and then the curve has a change of concavity at that point. At this point, there is a change of concavity. Now, how does that work? Let's do this exercise. Now here, I have all these lines. These lines is the slope, I'm going to show you how the concavity can change at a certain point. Okay? For example, this one. Follow me, follow me. This one, I'm going to draw a concave down through a concave up. So concave down and then concave up. That's the point. At that point, the line given to you is the slope. Not the slope, it's the tangent. Sorry, it's the tangent. This is the tangent. And the curve has a change of concavity at this point. Concave down, concave up. Okay? So there is a change of concavity. Here, this is the tangent. I'm going to do a concave down and concave up. How do I do it? Follow me. Concave down and concave up. Can that happen? I think it can happen in the curve. It can. Next one. Concave down, concave up. Down, up. Here it's down to up. Okay? So concave down, concave up. You practice with me. Concave up, down, and then up. Down and up. And then the last one. Down and up. How do I do that? Down and up. There is a change of concavity at every single one of these points. Next practice, let's do concave up to concave down. Concave up to concave down. Follow, follow. Concave up, concave down. So concave up, concave down. The next one. Concave up, concave down, concave up, concave down. It's not drawn well, but I want to make this the tangent at the curve. So concave up, concave down. So the tangent is vertical at that point. The tangent is vertical at that point, but the concavity is from up to down. Next one. Tangent is this way. The tangent is this way. Concave up and concave down. Concave up. Then down. The last one. Up and down. Up and down. So concave up, concave down. That's our first exercise. This exercise, in the past, I think that when you first encounter, now you just learn, you follow how I draw it. You just copy it, and then you feel, oh, this part is concave down, and then you tell yourself, oh, this part is concave down, and then this part is concave up. Then in the middle, there's a change. What I want to say is, I have shown you all 8 types of points of inflection because there is a change of concavity. Then these points are called points of inflection. Only the first 2, these 2 are called saddle points. Saddle points is one kind of point of inflection. One kind. Points of inflection can be different. As long as there is a change of concavity, then it can be called, that is a point of inflection. But a saddle point is a special one because a saddle point is stationary. Now, only this one and this one are stationary. These are not stationary, okay? But there's a change of concavity, therefore, points of inflection. Let's go back to the previous curve. The reason I drew so many curves is that, oh, you can have so many different examples to see. For example, this one, example 7. There is a change of concavity here, here, and here. There's a change. So in the middle, there is a point of concavity. The point of inflection. But this point is not stationary. Therefore, I don't call it a saddle point. I don't call it saddle. I call it point of inflection. Another example is the classwork on page 14. You see here on the left, it's concave up. On the right, it's concave down. So here, there is a point of inflection. Again, it's not saddle. It's not saddle. There is a change, but it's not saddle. It's point of inflection. Next one. Here. You see, on this curve, this part is concave up, this part is concave down. In the middle, there is a change somewhere. I don't know where, but there is one. There is a change. That is the point of inflection, and it's not saddle. This is not saddle. It's not horizontal, you see. This part is not stationary. It's not saddle point, it's just point of inflection. This curve, the whole way is concave up. There is no point of inflection on the other curve. Last example. There are many examples. Last example is this one. Here at this point, it's stationary and point of inflection. This one is a saddle point. If you get it, you will do this exercise perfectly. But we don't know. Now, please highlight the parts of the curve that are concave up in red. The part that's concave down in green. Afterwards, you can indicate all the points of inflection. When you are done, you let me know this exercise. Melissa, this time you're so fast. Oh, so you haven't finished. Melissa, hey, Christy. This part in red, concave up in red. This part is concave up. 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 Concave up. Concave up. The concave down part. Concave down. Concave down. Concave down. 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 And down. So the points of inflection are here. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. How many did you get? Cassandra, how many did you get?
I don't know why I accidentally drew across this on the extreme, but I got the answer.
You also.
Yes, I don't know why. Yes, but my coloring is right.
That's good. That's good because you improved. The last time you asked me the same question, you didn't know the existence of these ones. Remember?
Yes.
Now, long time ago, we talked about this, and at that time, I think a lot of students as well, they only realized, oh, the saddle points are those points, saddle points. But here, these ones are also points of inflection as you learn today. It may not be so easy to spot. Oh, there's a slight change of concavity because this part is concave down, although very short. Last time I also talked about, it's not about length. It's not about geometry. It's not about length. Even a tiny part can be concave down and then up. You see there is a change of concavity here and here. So you must realize not just 4 points of inflection, but many, many more. Many more. Now, to find the points of inflection, we need 2 steps. We need to find the second derivative and find out where it could change of the concavity. There could be. At when the second derivative is 0, all right. When the second derivative is 0 or undefined, does not exist. There's also a change of concavity when it's undefined. At undefined points, there is a change of concavity. That's possible. It's possible. And also afterwards, you would check if the sign of the second derivative is really changed from negative to positive. If it's not, then it's a false alarm. Right? It could be a false alarm, do you know? If it's like the first derivative test. If you find the stationary points, and it could be a saddle points, it's not maximum minimum. Because after the test, you will find out, oh, it's not. It's not. This one as well. You find out, oh, these points may be the points of inflection, but everything has to be confirmed before you draw the final conclusion. I'll show you. I'll show you. This one is a polynomial. So the first derivative, 4x cubed plus 6x squared minus 72x minus 30. It doesn't matter. I'm not looking for the maximum minimum, so I would not solve anything. So y prime prime 12x squared plus 12x minus 72. Okay, I will solve the second derivative equals 0. 12x squared plus 12x minus 72 equals 0. X squared plus x minus 6 equals 0. X equal 2 or negative 3. So you can find there are 2 here. Now on the graph, you're not given a graph, but on the graph, if you have one, you will find there is a point here, 2, negative 3 as well. Then you see the change of concavity there. I hope you can. I hope you can. But anyway, for this polynomial function, we don't have anything undefined. So we can skip that part. If you don't have anything undefined, then that's okay. And we will only be testing on these 2 points. The signs of y prime prime are as follows. Y prime prime. The first is x is smaller than negative 3. X equal to negative 3. Negative 3 is smaller than x, smaller than 2. X equal to, and x is bigger than 2. Okay? At these 2 points, the second derivatives are 0. And smaller than, it's not easy to test, so I will factorize this. You see? Okay? Now, smaller than means 12 times negative, so it's positive. Between is negative. Bigger than is positive. Now, I do this very quickly, but for you, you need to check each individual factor. Each individual factor. I'll work out the sign. Okay? And then you will see, oh, is there a change? I think there is, from positive to negative. You see? From positive to negative. From negative to positive. That means these are points of inflection. So my final step, when x equal negative 3, y equal 0, I think. I didn't do it, but from the graph, I think it's 0. Anyway, when x equal to 2, this one, I don't know what it is. I need to calculate. So 16 plus 16 minus 36 times 4 minus 60 plus 200, 28. Y equal 28. It's not joined to scale. I mean, it is joined to scale, but the x scale and the y scale are different. Anyway, let me check if the negative 3 is correct. 81 minus 2 times 27 minus 36 times 9 plus 90 plus 200. Negative 7, not 0, negative 7. Again, it's very close. It's very close. So the 2 points of inflection are points of inflection are negative 3, negative 7, 2, 28. Okay. Now you quickly finish the classwork. So I know you're fine with polynomial. Okay, the answer. Not much to say there. Also, I must mention that when you solve the second derivative equals 0, you should always consider if it can be undefined in some way, because those points are also possible. Anyway, that's it. That's it. On the graph, okay. What? Am I wrong in some way? I hope not. What? Oh. Sorry, let me make some changes. This is not 24, 48, 48, 4. I thought so. 4, 2, negative 2. 2, 2, 2, 2. And then 2, negative 2. Negative 70. 2, negative 70. Negative 2, negative 70. It's here. It makes more sense because it looks like the change of concavity is here. Right? It looks like this side. Right? And then the other side. Yes, there is a mistake. Oh, I thought so. Why is it the root? But anyway. Next example. In this example, I think we will see the other one. The other one. Find a points of inflection. All the points of inflection. Y prime. Y prime prime. This is equal to negative 2 over 9. Just for once. Just for this time, I write a fraction. You see, if you solve y prime prime equals 0, you will have no solution. Right? Because this fraction can never be 0. But does that mean there is no points of inflection? I don't think so. Because this second derivative is undefined at x equals 0. But y prime prime is undefined at x equals 0. And that point can also mean there's a change of concavity. I will check. The signs of y prime prime are as follows. x, y prime prime, x smaller than 0, x equals 0, x bigger than 0. And then 0, right? And then you put in a value that's negative. Essentially, it's, you can put in a negative value to test. You can put -1, -2, either one, and it's positive. I think so, positive. So this one is negative. So there is a change of concavity. Now, what does that mean? All these numbers, they look very abstract. Does that mean it looks like a point of inflection on the curve? You can look at the bottom. You see on the left, it's concave up. On the right, it's concave down. But it's undefined there. It's undefined. In fact, it's undefined for the first derivative. As you can see, the tangent is vertical at there. At 0, 0 is vertical. So it's very possible when it's undefined, but still. Okay? And the original curve is not undefined. The original curve is not a fraction, you see. This is not a fraction. The derivative is a fraction. The second derivative is a fraction. Only the derivative is undefined, and the second derivative is undefined at 0. But the original function is not undefined. That's why there is still a chance for that point to be a very special point. Okay? Therefore, 0, 0 is the point of inflection. Miss Chen, should we say y at x equals 0 is undefined, or its sign is 0? Y prime prime. Y prime prime. Oh, sorry. I made a mistake again. It's undefined. I shouldn't say 0 because it's undefined. Undefined. Yes. I shouldn't say it's 0. I was used to writing 0. It's not. It's not 0 this time. It's undefined. Even if it's undefined, can still have a change of concavity. Yes, Sophia. Undefined. Next one. This one, y prime. D high low minus D low high divided by low square. Simplify. Negative x squared minus 4, x squared minus 4 square. I think so. Should I simplify? I can, but I don't want. I cannot. I cannot simplify. Y prime prime. D high. Low. Minus D low. High. Divided by low square. Be careful. Be careful. Be careful. I will first deal with the sign. I should have in the past, but I didn't. Anyway, I will deal with the sign. So it's positive, positive, positive. Deal with the sign. And then take out x squared minus 4 and 2x. So 2x, x squared minus 4. leaving me negative x squared minus 4. And then 2x is minus 4 plus 2x squared plus 4. And x squared minus 4 to the power 4. Then it's 2x. This one is negative x plus 2x. That's x squared plus 8 plus 4 plus 12 divided by x squared minus 4 to the power 3. Right? I think so. I think so. So solving y prime prime equals 0. I have 2x times x squared plus 12 divided by x squared minus 4 cubed equals 0. X equals 0 only. I have one solution. I will test this point. I will. But y prime prime is undefined at x equal 2 and x equal negative 2. Okay, I will also check these two. Okay, and then my whole thing, very long. I will check the whole thing. X, y prime prime from x is smaller than negative 2, x equal to negative 2, from negative 2 to 2 to 0, x equals 0, x bigger than 0, smaller than 2, x equal to, and x is greater than 2. You see what I mean? All check, all check. This one 0 and these two undefined, undefined. Don't want to write undefined. I will just write across, undefined. And then check, oh, is it positive or negative? It's easy if it's factorized. So 2x, x squared plus 12. And then this is x plus 2 cubed, x minus 2 cubed. I think it's easy that way. Check each factor. So smaller than negative 2, it's negative, negative, negative. That's negative. Between, I think it's positive. Between, yeah, positive. Bigger than 0, it's positive, positive. Positive, negative, it's negative. Bigger than 2, I think it's positive again. Okay, and you can see the same thing on the curve. If you have one, you can see concave down, concave up, concave down, concave up, isn't it? It's consistent. It should be consistent. Anyway, however, although there is a change of concavity here from here, now because the original function is undefined, y equal the original function, x over x squared minus 4 is undefined at x equal positive or negative 2. Therefore, there are no points of inflection at these two places. The only one, the point of inflection is 0, 0. It looks like we did nothing about the, but I think it's important because it helps with understanding the whole curve, because later on you will find out the whole curve. So there is a change of concavity. Let me just put this, there is a change, but there's no point there. So there's nothing there. It's nothing. It's blank. And here there's blank, but here there is a change. And also, I don't think this one is stationary. Is it stationary? It's not. You can see at 0, this first derivative is not 0. First derivative not 0. Second derivative 0. Okay. So I just want to show these 2 more examples to show you, why undefined and still go check for those points. Why? And there is a need. You will do the exercise and then you tell me your answer. Now I'm not going to do it just in case I make a mistake again. So embarrassing. Okay, look at the answer. The first one, the second derivative is a fraction. It doesn't have equal to 0. It doesn't have this 0 point. So it's only undefined at x equals to 2. There is no step showing solving, but you can see there is no solution anyway. So we skip that and then say, oh, this is undefined. And after checking, we find out this point is actually a point of inflection, although undefined at the second derivative. In the second derivative, it's undefined. Second derivative. This is boring. Derivative. And then the second derivative. You do it twice. Each time you have to apply the quotient rule. Again, the key is to factorize, not expand. So here the factorization. And there are 3 points. They are very sus. X equals 0 and the 2 undefined. And then check the signs. After checking the sign, we know this one is a point of inflection. But it says it's broken. It's actually, this word is used in the textbook. I say it's undefined. It's broken as well. Broke, discontinuous, broken. So there are no points there. It's a very similar situation to this graph. There is a change of concavity, but there is no point. Okay, that's all. That's all. You have to take this lesson very seriously, because in the past, I feel that some of the students don't understand it's like all of the concepts are put together and somehow it's a blur. You shouldn't know. You shouldn't know. For the first derivative test, that is designed to find out maximum minimum. For the second derivative test, also find maximum minimum. For the points of inflection, it's completely different, because I don't look for the stationary points anymore. I don't care what the stationary points are. I'm checking for the concavity. I'm not checking for the slope. You see the first derivative, I'm checking the slope. Is the slope positive? Is the slope negative? Right? Now I'm now checking, is the curve concave up or concave down? I think as soon as you can tell the difference between checking slope or checking concavity, then you can have a better understanding of the curvature. Is that okay? I don't know how the absentees are gonna make this up before Monday, because on Monday we're going to continue. Chapter 6 is very hard, girls. It is. It's not just in the example I give you the simplest function to differentiate, like polynomial, right? What is there to differentiate? It's like you can do it in 1 second. So you see the whole chapter 5, we study it. We can differentiate. We can actually differentiate very difficult functions, but we don't ask you to analyze those curves. We just analyze the simplest one, like the polynomial, the fraction, and sometimes a little bit trigonometry. Right? Now, what if I give you an implicit function? Is it possible? I think it's possible, right? If I design the function and then it's very different from polynomial, and it's even like a mixture of something, then the differentiation part will get harder. But nonetheless, the core concept of how to look for the minimum maximum, how to look for the points of inflection, still unchanged, still the same. You still look for stationary points, you still test those stationary points, you still look for second derivative equals 0 or undefined, you still test those points. And in the end, when you put all the points together, and then you can sketch the curve. That's our ultimate goal, to sketch the curve. That's all. That's all. Watch the video if you're done with the exercise. Bye-bye.